Hello students. Today I am going to start a new topic which is called the transient analysis. Okay. This is also important topic. So far we have done the steady state analysis. Okay. So in this class we will going to study about the transient analysis. Now first of all, let me clear what is a transient analysis. Now when you apply an input, okay, and so far the numericals you have solved either in AC or DC, you always assume that yes, you have applied the input and you have immediately got the output. But mind it, that output is not so easy, especially in case when inductor and the capacitor are present. So when inductor and capacitor are present, there is some time lag is there in reaching the final value. So the final value is called the steady state value. But in between, what is happening? Okay, in between the starting time and the reaching the final value, there is a period, and that period is called the transient period. And we have to find out what will the behavior of the system during this transient period. Okay, so let us discuss today that what the things are. I must open the first of all my so this will be recorded. Therefore, those who could not attend, they can see on the YouTube. No problem is there. But since for many days I am not available, therefore I am today will be delivering all the lectures which will be coming in your course. Okay. So the today's topic is the transient analysis. Now you might have gone through in mathematics the so-called the differential equation. Okay, so differential equations come whenever there is a something dynamism is there. Okay, some dynamism, that is the things are varying with respect to time. Okay, so this type of equation you are very much familiar. Tau dx by dt plus xt is equal to ks ft. Okay, and suppose that the initial condition at any time is something x0 at t is equal to 0, and then we solve this differential equation. Then we have two parts of the solution. One is called the homogeneous solution. The homogeneous solution is obtained by equating this part, that is the input is made 0. This case ft is the input. So if it is made is equal to 0, we are left with the equation tau dx by dt plus xt is equal to 0, and when we solve it, we'll get and a homogeneous solution. And then we find out the particular solution, which is also called force solution. So this natural solution plus force solution will give you the complete solution of the given differential equation. Okay, so here we will apply how it is useful, how it can be useful in our so-called circuit theory. Okay, so we have to remember that there are two solutions for a differential equation. So similarly, so far we have talked about the steady state analysis. Okay, you directly give, 5 volt is being applied, 2 ohm is resistor, so 5 divided by 2, 2.5 ampere. Similarly, for the inductor case, okay, if it is given a 5 volt AC source is being applied and the impedance is J2, then you say 5 upon J2. So when you say 5 upon J2, mind it, so basically whatever current value is coming, this is volt and this is your impedance ohm. Okay, so you will get certain minus 2.5 J. Okay, like this type of value you will get. So this is the steady state value. Okay, this is not the transient value. Okay, this is the steady state with the final value you will obtain. But we want that before reaching 2.5, it might have gone to 0, it might have gone to 1.5, it might have gone to 2, then 2.2, and then ultimately reaches 2.5 ampere. So what path it has traversed? What path it has traversed? Path traverse with it be exponential. It may have rise like this. Okay, suppose this is the graph time versus. Okay, it will might have reached, or it will might have reached like this also. Like this also. So we want to know the behavior that in reaching the steady state value, what path the what graphical approach the system has used in reaching the final value. So and mathematically we obtain by solving the differential equation. Okay, so this is one such differential equation is presented before you, where the first order differential equation was presented. So as I already told, a differential equation from mathematics point of view have two solutions. One is called homogeneous solution and another is called the particular solution. The homogeneous solution in our electrical engineering is known as the transient solution. Okay, and the particular solution is called the steady state solution. Okay, so whenever I tell you find out the solution of this equation, it means I want both solution. What is the transient part and what is the steady state part of a given differential equation, which is representing the a particular electrical system. So it is very clear that first of all we have to frame out the differential equation. So far we were writing only algebraic equation. Mind it, please keep in mind that so far we were writing only algebraic equation, but now onwards we will be writing the differential equation. So we first know the what are the differential values of the different elements being used in the electrical engineering. You know, three basic elements are there: our resistor, inductor, and capacitor. So we should know how to represent it in a time domain form, these three. Okay, so this is just a way of representing the how to find out the natural response, also called the homogeneous response, and in electrical, which is also called the transient response. So what you do that you make this part, okay, the left hand side of your right hand side is made equal to 0, and so the equation left behind is this, and in fact this right hand side is nothing but the your excitation or the input which you have applied on the system. Okay, it is made equal to 0, so it is basically a zero input response. It is also in some books you will heard that it is also called a zero input response, the homogeneous solution, also called natural response, and in our electrical terminology it is called the transient response. It is called the transient response. So when you will solve it, okay, by the differential equation technique of mathematics, you will find that the natural response or the transient response comes out to be alpha e raised to a minus t over tau, where tau is known as the time constant of the circuit. Okay, so this type of response is called natural response or transient response, or we can also say the zero input response. Okay, so be aware of all these things. Okay, then next comes the force response. The force response is the response which is obtained when the input is being applied with cap. So the excitation is capped. So let us just make this as F. Then you solve it. When you solve it, you will get a certain solution. Okay. Then the solution is called the force response. And when you combine these two responses, you will get the complete solution of a given differential equation. Now this equation will be representing a some system which may be mechanical, which may be electrical. Since we are from electrical engineering, so we are basically interested in the electrical engineering analysis. So as I've already told you that this so-called the response, okay, this part, this response is called the transient response, as already told you, and this response which is obtained, which is the final value, or in fact, people say that the response obtained at infinite time. Okay, that is infinite means a long time. So that is called a steady state response. How the graph will look like. So some graph has been presented before you. Let's see. In this way, the transient response is like this. It is initially 0, then increasing, then exponentially increasing, and then settle down to a final value, okay, which is less than 1. Now it can be like this. For example, previously there are some oscillation are there, okay, which are oscillating at different frequency, and later on they settles down. So these are the transient oscillation. This is the transient sinusoidal voltage, the previously transient DC voltage. Ultimately it will become a constant value, so it is called transient DC voltage. Ultimately it will become a sinusoidal waveform, so it is called transient sinusoidal voltage. that where we will come across the transient analysis. The first case will be there when a DC voltage is being applied to a circuit containing R as well as the energy storing element. There are two energy storing element, that is L and C. So if R is being connected with either L or C or RLC or this, we will come across this type of transient analysis and a DC voltage is being applied to it. Okay. So here you cannot always, there will be a one switch. Okay. Because the switch is very important. What is the situation before applying the switch and what is the situation after the application of the switch? So that is very important. So you will see this type of figure. This type of figure is there. A 12 volt source is being applied to an load which contains R as well as L and C, and they are being operated to a switch. So whenever you make the switch on, that time will be referred as a t is equal to 0. Okay, and you will be asked to find out the value of the system for t greater than 0. Mind it, for t greater than 0. Okay, and there can be a situation that what is the value of the circuit for t less than 0. So t less than 0 means any value, any voltage across the capacitor C, any current through the inductor L will be termed as an the initial values. Okay, the initial values, that is which is present less than t0, that is before switching on the switch. What is the value voltage across the capacitor C and what is the current flowing through the inductor? In many cases you will find it may be 0, there is no voltage across this capacitor, there is no current flowing through inductor. Then we call such type of system as initially relaxed. We'll call such type of system as an initially relaxed system. But there are certain questions which are very important from transient analysis point of view, where we have some capacitor across C, where we have voltage across capacitor C, and we have current through the inductor. And in mathematics point of view, these are called as initial condition. These are called the initial condition. And while solving the numericals for transient analysis, okay, we have to take into account these initial conditions. So we have to look into the question, the circuit, very carefully, or in the data also. Sometimes these initial conditions are given in the question itself, and sometimes it is given in the diagram itself. Okay, so we have to carefully examine the diagram as well as question. Is there any initial condition is there or not? Initial condition can be only on capacitor and inductor. In capacitor it can be voltage, and in inductor it will be current. So you have to be very cautious. So these are the two examples which I have shown you. Okay, that there we will go for the transient analysis. So what will happen? A voltage source is there, a DC voltage source is there, a resistor which is internal resistance RS, and a switch is there. Now this switch is closed. If arrow is like this, it means it will be closed at t is equal to 0. If arrow is like this, mind it, then suppose t is equal to 0 is written and arrow is like this, is pointing going outward, it means that at t is equal to 0 it will be opened. So you have to be very cautious regarding the arrow sign also, that if arrow is moving downward, it means the switches will be closed at t is equal to 0, and if arrow is pointing going outward, then it will be termed as an this switch will be opened at t is equal to 0. So these two things you have to keep in mind, that there will be some DC source will be there, and the circuit will contain either RL or RC or RLC can be there, and you have to find out both the transient analysis as well as the steady state analysis. So you have to write down the differential equation of this circuit. So far you were writing the algebraic equation. In finding out the steady state solution, you were writing the algebraic equation, but now in the transient analysis, you will be writing the differential equation. So mind it, so the whole game is on the differential equation. So now let us understand what our this different elements possess. Okay. So first of all, this is just a numerical has been put before you. Okay. Let me clear whether I have included or not. Okay, so before proceeding this, let me clear first of all here only that how the circuit will behave for in a from time domain point of view. So first of all, take the resistor case. Okay, first of all, I will take the resistor case. So in resistor, if you apply a voltage, then from time point of view, it will have an instantaneous behavior. That is Vt is equal to RIT. Okay, so this is the behavior of the resistor, that is instantaneous behavior. As soon as you apply the voltage, it will start flowing the current. Okay, and from time domain to Vt is equal to RIT. This is the first equation you have to remember. Now, come the second equation. Okay, what will be the behavior of the inductor? Now, inductor, the voltage current relationship in an inductor from time point of view, it is Vt is equal to L di by dt. Oh, you have to remember this. Okay, so whenever you write down the differential equation, initially relaxed inductor, mind it. What I am saying, initially relaxed inductor will be initially relaxed means there is a no initial condition. There is a no initial condition is there. Okay, so that inductor will be represented by its voltage current relationship is represented by Vt is equal to L di by dt. Next come the capacitor C. Initially relaxed capacitor means there is no voltage across the capacitor. So that capacitor will be represented. I will represent it current I is equal to C dV by dt. Okay, so I can write down V is equal to 1 C integral I dt. Is it clear? So this is the voltage current. Similarly, you can find out the current relationship also. Here current relationship for inductor will be I is equal to 1 upon L 1 upon N integral V dt. Okay, but here in case of capacitor, I is equal to C dV by dt and V is equal to 1 upon C integral I dt. Okay, so it is very clear from here that the voltage across 1 upon C is equal, voltage across the capacitor is 1 upon C integral I dt. Now, again and again, I am stressing that I am writing these equations for capacitor and inductor, assuming it that they are initially relaxed. Now, if they are not initially relaxed, then how it will be changed? So let us look into that matter also. Okay, so when they are not initially relaxed, okay, so what will happen? Initially, when inductor is not initially relaxed, it clearly means that some current is flowing through it. Okay, so my I, as I already written it, that I will be in case of will be 1 upon L is equal to V dt. Okay, so definitely there is some initial current is there. Okay, so I will write down an I 0 minus. Now this 0 minus is indicating that the initial current flowing through the inductor. Okay, the initial current flowing through the inductor. So when I will write down in the terms of the voltage, can anybody tell me that what will be the voltage value? What will happen that there will be some current flowing through is there, and therefore when some what will happen if I will form this in the current form in the form of voltage? Okay, so it will be nothing but let me check me. Okay, I minus I0 is equal to 1 upon L integral V dt. Okay, it will be like this. Oh, okay, so L will be go there. Okay, and ultimately you take the differentiation and you will get the value. So what happens? A current source will be added in the current source of value I0 will be added with the with the inductor in case when some current is flowing through it. Now let us take the case when some voltage is there. Okay, so what will happen? Suppose V is equal to, sorry, we know that I is equal to C dV by dt. Yes. Okay. So now here a voltage is present. So I will change into, because capacitor accumulate the charge and thereby create a voltage. So my V will be equal to how much? 1 upon C integral I dt. This was the case when the capacitor was initially relaxed, but now some initial voltage is there. Okay, so I will represent it by V0 minus. Okay, so that's how the equation will change. So in the differential equation, when current is flowing through a conductor, then how will you manipulate the current and how will you manipulate the voltage? That the two equations I have given you regarding the how to write down the equation, the dynamic equation for an inductor and a capacitor. While for a resistor, whether it will always remain initially relaxed, it will behave instantaneously. Vt is equal to R it. Okay, so let us write down one equation. Okay, so sorry, a voltage source is being applied across a resistor and a capacitor. Okay, and these capacitors are initially assumed to be initially relaxed. So Vs, what I have will write down. I am taking this circuit. So Vs T is equal to, now this equation is balancing drop across this inductor resistor, and which is nothing but I R into capital R, because it will behave instantaneously. We have already IR here is the IR is rather than being a same circuit, therefore I can represent it I. So instead of IR, I should write simply I. Okay, and therefore IT, rather I think right, ITR. This is the drop across the resistor. Now come the capacitor. Capacitor is initially relaxed. Okay, so no voltage across it. So I will assume no voltage is there, and I will write down its what happened. I will write down its voltage, because voltage drop across it, and the voltage drop across is nothing but 1 upon C integral I d E. Okay, the current is through this is I. Okay, so now mind it, it is always difficult to solve an integral equation. Okay, a circuit equation containing some integral component. So what we will do, we will convert into differential equation. So here an integral term is there because of the capacitance. So I will take the differentiation of both the sides. So what I will get, d Vs by dt. I am omitting the time t. Okay, the Vs is already indicating that it is a function of time t. Okay, so I is there. Okay, I will become, because I is also variable, therefore it will become di by dt multiply by resistor is a constant, nothing. Now here the integral will change. Now since there is no voltage across it, therefore it will become 1 upon C I. 1 upon C I. So this is the equation. Okay, and now you can the same equation d. Now since it has taken and term IC, so here you can see now one more important thing, that always the degree, highest degree coefficient is made unity. So here it is R. Highest degree of differential is 1. It is the first order. So here its differential is here its coefficient is R. Therefore I will divide the whole equation by R, and what I will get ultimately, RC, and here also 1 upon R. So it will be di by dt plus 1 upon IRC is equal to 1 upon R dVs by dt. So this is the equation. So the first of all, the first practice is to obtain the equation of the given circuit. Okay, if you are able to get it, then it is well and okay. If not, then your whole solution will be wrong. So the first and most important topic in this is to obtain the differential equation by taking into account all the things. The initial conditions in electrical engineering are nothing: the voltage across the capacitor and the current flowing through the inductor. Now now let us take this circuit. Now let us take this circuit. Okay, though this circuit is also there, I have skipped out this circuit. You can write down the differential equation. So let us practice it. Okay, you may feel some problems, so I will just have a practice like this. Like, take this example. Previously we have taken this example, how to write down. So Vs, I am not writing in the bracket T, it is explicitly mentioned. Okay, it is there. So let the current flowing through it. So use my way. Let current flowing is I1. Let current flowing through this is I2. Okay, so we have solving through the mesh analysis. So Vs, how much current is flowing through the IR1? So Vs will be equal to I1 R1. Okay, instantaneous. Now this is inductor is there. Okay, mind it, inductor is there. Now in inductor, two current are flowing. One is I1 and another from the downward I2. So the Kirchhoff laws will remain same. No change is there. Only the way of writing the equation is different. So L di by dt. So instead in di by I is nothing but I1 minus I2. So like this, you will write down this equation. Okay, so this equation is complete. So this is equation number 1. I think so it is very clear. Okay, now next come the second equation in this mesh. Okay, so let us start from here. What I will get? Minus R2 I2. Now I2 will be there. So what will be there? Minus L bracket I2 minus I1 upon, oh sorry, here I d by dt, and this equal to 0. Okay, so you obtain two equations. Okay, first and the second equation, and the rest thing is that you have to solve these two differential equation in order to obtain the I1 and I2. So it is very clear how to write down the differential equation. The first step to practice is to write down the differential equation. Okay, now here the two example which I have taken, I have assumed the initial condition to be 0. Okay, so let us move to the some more things related to this. Now, I have already told you that there are some case where you will come across the some initial conditions also. So how these initial conditions in some questions directly in the book only it has been motion, assume an initial voltage across the capacitor of 4 volt, or assume the initial current through the inductor is 2 ampere. But in some question which are being considered as a typical question, okay, the person who is solving the numerical, he himself has to find out that is there any initial condition is there. For example, the question which is in front of your screen is one such question. The circuit at t is equal to 0. Okay, same circuit. Now we have taken the two cases. First of all, when the circuit at t is equal to 0 means this switch is closed at t is equal to 0. Okay. Now the same circuit a long time after the switch is closed. Okay, so there are two behavior is there. Okay, what will be the behavior of the circuit at t is equal to 0, and what will be the behavior of the circuit after a long time? So you have to understand these things. Okay, then only you can find out the initial condition. So I will take three elements. First of all, rather than going to this numericals, I will first of all explain through my elements. Inductor. Now inductor behaves, sorry, inductor not resistor. Resistor behaves instantaneously. I have applied a voltage, it will immediately current. It will immediately give the current. And if I have removed the voltage, it will immediately reduce the voltage to current to zero. So it has immediate behavior, instantaneous behavior. So no problem. Nothing to be worried about. It never stores. Now it only dissipates. Okay. And what about the inductor? Now take the case of inductor. Now, if I apply a voltage, suppose this initially relaxed, okay, and now I apply a voltage, DC voltage across the inductor, okay, through a switch at t is equal to 0. So at t is equal to 0, mind it, I am asking at t is equal to 0 at the instant I have just switch on the circuit, what will be the behavior of the inductor? Now mind it, this you have to keep in the mind. At t is equal to 0 instant, the inductor will behave as an open circuit. ये जो हमारा इंडक्टर है ना, इसकी एक बहुत खास विशेषता है कि बहुत है ना धीरे धीरे चलता है. ठीक है, ऐसा नहीं है कि आपने वोल्टेज लगाया और इमीडिएटली करंट दे दिया. अभी तक हम जो करंट निकालते थे ना वो स्टडी स्टेट की निकालते थे, लेकिन अगर हम इसका उसी समय बिहेवियर देखें, अगर एक इंडक्टर कॉइल के अक्रॉस अगर हम एक वोल्टेज सोर्स, डीसी वोल्टेज सोर्स लगाते हैं और जैसे ही हम इसको ऑन करते हैं तो इंडक्टर पहले तो उसको कहेगा नो, I don't want any current. I don't want any current means it will behave as an open circuit. So at t is equal to 0 instant, okay, this inductor will behave as an open circuit. So your circuit will look like this. At t is equal to 0, inductor will behave as an open circuit. Mind it, it will not allow the current to pass through it. But as the time progresses, okay, it will say, okay, just like you people have also behavior. If something new comes, always people oppose it. Oh yeah, what this nonsense has come, I don't want. But later on, when it is coming repeatedly and repeatedly, you accept it. Okay, the same behavior is of the inductor also, that initially, when a voltage is applied, it will oppose it. It will not allow the current. So at t is equal to 0, it will be an open circuit. And after a long time, it will behave as a short circuit. Mind it. So long time means at infinite. In mathematics, we tell, and after infinite time, or in a more precise manner, in after a long time, that is when a time of 1 or 2 minutes has elapsed, then we will see that the inductor, same inductor which was initially behaving as an open circuit, now after a long time it will behave as a short circuit. Okay, so here the two terminals will be get closed. Okay, so after a long time, if a DC voltage is applied across a pure inductor, it will behave as a short circuit. Mind it. Okay, so always it is being told that always apply and resistor in series with an inductor, because after a long time it is going to become a short circuit. Okay, so never do this thing. Always apply a series resistance in with the inductor. Now let's talk about this is all about the inductor and resistor. Resistor instantaneous behavior, while the inductor at t is equal to 0, it will behave as an open circuit. At t tends to infinity, it will behave as a short circuit. Okay, so let us take about the capacitor, the third case. Okay, capacitor. This now let us assume a capacitor is connected across a DC voltage source. Sorry. Okay, a switch is there. Suppose a switch is there here. A switch is there. V voltage switch is there. Okay, now at t is equal to 0, as soon as I will close the switch, at t is equal to 0, the capacitor will behave as a short circuit. Mind is just opposite to the inductor. Okay, inductor opposes the current, while the capacitor opposes the voltage. So it will behave as a short circuit. Now you applied a V voltage across the capacitor. Okay, so capacitor, I don't want it. I don't want it. So it will have, what will do at t is equal to 0, it will get short circuited. So at t is equal to 0, initially relaxed capacitor behave as a short circuit. But after a long time, when system will settles and everything will settles, okay, then at t tends to infinity. So this is the behavior of the capacitor at t is equal to 0, while at t tends to infinity, okay, the same capacitor will behave as an open circuit. Why it will open circuit? But what happens later on? What will it capacitor will do? This capacitor will do nothing but it will acquire the same voltage as that of the applied source. Okay, so applied voltage is V, then it will also acquire V. When voltage are equal, there is no chances of flowing of current will become 0, and therefore this will be termed as an open circuit. So at time t is equal to infinity, the capacitor behave as an open circuit, while at time t is equal to 0, the same capacitor behave as an short circuit. Is it clear? So I think so these two things are very clear. Okay, the resistor behave as an instantaneous behavior, the capacitor behave as an at t is equal to 0, it will behave as short circuit, while at tends to infinity, it will behave as an open circuit. Similarly, for the inductor, at t is equal to 0, it will behave as an open circuit, and at t tends to infinity, it will behave as a short circuit. So these three things you have to keep in the mind every time. Okay, every time when you solve the numericals, you have to keep these three things in the mind, in addition to the corresponding dynamic equation of each element. Is it clear? I think so. These concepts should be kept in the mind while solving the transient analysis. Now let us take this example. So what is happening here? At t is equal to 0, okay, as soon as I will close the circuit, okay, how my circuit, this A circuit will look like? This A circuit will look like at t is equal to 0. So at t is equal to 0, the capacitor will behave as a short circuit. So when I will draw the, if I will, somebody asks me what will be the value of this circuit at t is equal to 0. So I will say, okay, sir, no problem. You have closed the switch. R1 is there, R2 is there, and now this capacitor will behave as a short circuit. So I will just short circuit this capacitor, and here I will connect another resistor like this. So my circuit will be simply R1, this will be R1, okay, this will be R2, okay, and sorry, things as well, and this will be R3. Okay, so now take the case, the same circuit. What will be the behavior of the circuit? How the circuit will look like at t tends to infinity? So at t tends to infinity, what will happen? Okay, this capacitor will become open circuit. This capacitor will become open circuit. So what will happen? It will be open, and therefore you will left with R1, R2, R3. So it is very easy to solve it. There will be no current will be flowing through this. So the current will be VB upon R1 plus R3 at after a long time, that is at t tends to infinity, and the value of this value is known as steady state value. That is the value obtained at t tends to infinity is being termed as a steady state value. I think so it is clear. Okay, now let us take this case. This I have taken now inductor case. Okay, so now see, I have already told you that you have to be very cautious. You have to be very cautious in seeing the arrow. Okay, so what will happen? So in this circuit, okay, let us say that the switch has been closed at t is equal to 0. Okay, or at t is equal to 0, the switch is already being closed condition. Okay, in closed condition is there. Now, when the switch is in the closed condition, initially at t less than 0, so this inductor was behaving as a short circuit, because we assume that a long time has been happened. Okay, a long time has been happened. Therefore, definitely it will settle to a steady state value for t less than 0. So at t is equal to 0, okay, this will behave as an short circuit. So when I will close the circuit, the inductor will behave as a short circuit. Mind it, I have told you that had it been like this, I just made don't get confused. Had it been like this, my circuit would have like this. Okay, then because initially there was no source was there was no source was yes, in this there are two sources are there. Sorry. So now what happens that the circuit is, I think so, the it was being drawn not in a proper manner. So let me clear the things. Okay, so at t is equal to 0, the switch is closed. Okay, so previously this switch was open. Okay, this switch was open. So current was flowing through the inductor because of this circuit, and we assume that the final steady state has arrived. So when I will close this circuit at t is equal to 0, my inductor will behave as a short circuit rather than the open circuit. Okay, now take the case, suppose this was not this was not there, it was simply I short circuited. Okay, now since there was no current flow flowing through it, so when I close this switch at this point at t is equal to 0, at that time my inductor at t is equal to 0 will behave as an open circuit. Okay, mind it, you have to keep in this thing in the mind. Okay, the inductor will behave as an open circuit. So I have already told you that voltage across a capacitor cannot be changed instantaneously, and that is why the capacitor behaves as a short circuit at t is equal to 0. Similarly, the current across an inductor cannot change instantaneously, and that is why the inductor behaves as an open circuit. Initially relaxed inductor behave as an open circuit. Okay, so let us take an example. Okay, so at t is equal to 0, the switch is being closed. So let us first of all find out. Sorry. This was the already circuit was there, and at t is equal to 0. At t is equal to 0, the circuit, this switch is moved from this position. So let us mark the position. Okay, this is say 1 position, this is 2 position, and this is 3 position. So what the question is there, let me clear the things, that at t less than 0, for t less than 0, okay, the circuit was at t less than 0, mind it, the switch was between 1 and 2. Switch was closed between 1 and 2. So this was the position. And at t is equal to 0, the switch was moved from 2 to 3. From 2 to 3. So at t is equal to 0, the switch has moved from like this. Okay. So now the question is how to solve this question. Now they will ask you find out the IL. They will ask you find out the IL. So what will happen? Initially, when for t less than 0, okay, this IS current was flowing through it, okay, through inductor as well as resistor. Okay, now for t less than 0, whatever may be the condition, we will assume that the circuit was in steady state condition. So under steady state condition, the inductor behave as an yes, anybody can tell me, inductor behave as a short circuit. So what will happen when it will get short circuited? Okay, so this resistor will short circuited, so the current IL 0 minus will be nothing but equal to IS. This is the initial condition of the inductor. Okay, that is whatever the source current is there, that is flowing through the inductor being the short circuit. Okay, so IL 0 minus is nothing but IS. So in this way, by looking towards the diagram, you have to find out the initial condition. So this is the initial condition. You have to find out that this is the initial condition flowing through it. Now, don't forget this initial condition. Okay, we will utilize this initial condition. Okay, now at t is equal to 0, so all the things which I have told you, that IL0 is equal to IS, this was the situation at t is equal to t less than 0, or also at t 0 minus. Okay, now at t is equal to 0, my switch has moved from 1 to 3. So what happens, that my inductor and resistor circuit are completely devoid of any source. It has been cut off. It has been cut off. But still I am asking, what is IL? So naturally a layman will say, since no source is there, so no current will flow through it. So current through IL is 0, and that is the answer. No. This is not the answer, because the current, initially it was having some current, that is IS. Okay, it has stored at some current IS, and now this IL0 minus will play an important role. So how it will play an important role? So when I will write down the, so I will already told you that now when you will draw the circuit, this is the circuit. Okay, it will not only have a L, it will have a IL0 minus only. And what is the value of this IL0 minus? This is IS. So this IS will behave as a current source. This will behave as a current source. Okay, so current through the inductor will behave as a current source, while the voltage across the capacitor will behave as a voltage source. So tomorrow, how to insert that current source in the circuit and the voltage in the circuit, that we will deal tomorrow. Okay, so for today's being, it is very clear that now we have, for transient analysis and steady state analysis, we have to write down the dynamic equation, that is the time domain equation, and we have to also take into account the behavior of the inductor and the capacitor in the different situation. Okay, so that's all for today. Tomorrow we will take some more numericals related to transient analysis.